Hello, everyone. Welcome to our second WITS P&ATS webinar event titled Using Data to Manage Well Integrity. My name is Pierre-Edouard Vincent, and I'm with the P&A technical section. My fellow WITS officer, Jovan Stojkovski, and myself will be your hosts and moderators today. The event will last 60 minutes, but will not have a hard stop. We encourage you to ask questions throughout, which we will use to fuel the discussion. Most of you will be joining via LinkedIn, but if you're experiencing technical difficulties, you can also use the alternative YouTube link provided on the LinkedIn page. I've entered that earlier today. The event will be recorded and available on demand on our various platforms. Note that there will be a follow-up session. The date will be announced later to cover the entire topic, so in two parts. As an intro, before we start, I would like to invite you to consider joining SPE and access the many benefits of being a member, and also joining our technical sections for well integrity and P&A, both available through SPE Connect and LinkedIn. A couple of updates from us. So Jovan, over to you.
Thank you, Pierre. Welcome everyone. And before we start with the interesting topic today, I would like to advertise and give opportunity for everyone who want to attend and participate on ATCE. This year will be held in Houston, Texas in 20 to 22nd October, and encourage all of you to submit your papers. Deadline is 3rd of March. So by submitting a proposal, you will have, of course, opportunity to share the knowledge and expertise, influence the technical program during the ATC, and lead a technical session as a speaker. Become published author in the One Petro and be seen in the industry as an expert. But last but not least, and to be a part of historic legacy that continues to shape our energy sector. Today we have a really interesting topic. Today's speaker, Danilo Colombo.
And I have two more. I have two more updates to give, Jovan. So there will soon be a young professional event in Paris that will happen on March, or end of March. I think it's 19th to 23rd. And if you are a member of SPE and within that category for young professionals, this is a Beyond the Borders event, which will gather young professionals potentially from various regions, and you should consider joining. It will be a great event that will also coincide with the 40th anniversary of the SPE French section. And finally, the team for the 25 AWEL SPE Europe Well Integrity Workshop is now getting busy preparing for another great event. This will be held in Q4 in Amsterdam, same venue, and we strongly encourage you to try and join us there. There will be limited availability. And over to you for the introduction to Danilo.
Thank you, Pierre. Today, speaker Danilo Colombo is a mechatronic and petroleum engineer, which serves as a technical advisor and reliability and risk assessment at the Petrobras, and research coordinator at the Petrobras Research Center, where he has been leading R&D project for over a decade. Danilo holds a PhD in the machine learning applied to reliability, as a master degree in the well integrity and the management system, and MBA in investment management. He's also currently enrolled in the data science specialization. He's certified as a reliability consultant by Compass, and he's developed thousands of computer programs and has published extensively, including hundreds of papers, books, chapters, and presentations at workshops and congresses worldwide. Additionally, he teaches disciplines such as well integrity, reliability, and risk assessment. Danilo is also a member of the Brazilian Association of Risk Assessment, Reliability, and Process Safety, the Society of Petroleum Engineers, and Brazilian Petroleum Institute, where he's currently coordinating the development of Brazilian guideline for the risk assessment for the wells. So please welcome to our speaker, Danilo. Danilo, I will hand it over to you for the interesting topic, which is using data to manage well integrity.
You've been muted. You've muted yourself, Danilo. So.
Oh, sorry. I was talking muted. Common mistake. So, good morning, good afternoon, or good evening, depending on where you're watching. Thank you very much, Jovan and Pierre, for inviting me to this webinar. It's a great opportunity. And I'd like to say that I appreciate your efforts to organize these events. I'm watching them all, and they have been very interesting. So today's topics, I will be divided, as Pierre mentioned, it will be divided in two parts. The first part today, I'm going to talk a little bit about quantitative risk assessment and its role in the well integrity management system. In the next webinar to be defined, I will be continuing to discuss reliability in a broad way. I will going to talk about reliability, availability, maintainability, and safety. So we can see how we can use these concepts from the design until the remaining useful life of the well, and even to plan P&A campaign. So today will be part one. Before I jump in my presentation, I would like to ask a question that will help us set the scene. Or as someone who loves the show, let's play Who Wants to Be a Millionaire? So the question is, what is the proportion of wells worldwide with integrity issues? A, less than 10%, between 10 and 25%, between 25 and 50%, or more than 50%. I will give you a few seconds so you can think about the answer. And you can try to guess, you can try to put on the chat, but the answer is letter C. So whoever answers C got it right. It's estimated that around 1/3 of wells worldwide present integrity issues. I must confess that I first saw these numbers, I was scared. So it's a huge number. 1/3, one every three wells have has integrity issues. And obvious, not all those wells impose an imminent risk of blowout, but around 1/4 of those wells are closed, which represents a huge production loss. Besides that, intervention would be necessary to repair most of these wells, represent an enormous cost, and the same goes for the ones that will have to be permanently abandoned, leading to the necessity of drilling new wells. So this isn't just a question of $1 million, it's a $1 trillion perhaps question. And it tends to worsen in the future with the wells aging and the new frontiers with thermal wells, CCUS, etc. So it's a quite challenge. And with a problem of this size, I would imagine that companies using machine learning, robots, quantum mechanics, or any complex simulations to know what to do with these wells. But do you know how most companies manage well integrity today? I can't say for every company, but the ones I've been discussing for many years, most of them are using system based on the integrity status and a color system such as this one. They can be more sophisticated, but they have basically a few categories to classify the wells. And stay with me now. For the wells that are in green with no failure or minor failures, we don't need to worry about. The wells in red, of course, they are the worst, but we don't need to worry about decision making either, as we must act as soon as possible. So we end up with only two categories to classify almost 1/3 of wells that have integrity issues. So we cannot know based on this how to prioritize our resources, how to decide which wells must be closed and which wells could continue to produce. We don't know how much time we have to plan a recovery, or the so-called grace period. We don't know if you can extend the life of a well. We cannot answer a lot of questions using this model. And the system used today was an evolution at the time, and it is still important, especially regarding compliance and communication. But it has evolved much over the years and presents a lot of limitations and opportunities for improvement, such the categorization. As I mentioned, we have few categories to classify the wells, only two that matter. And the reason is that it uses well bearer as a management unit. The well has 2 barrels, 1.5. The well bearer is not a measurement unit. 2 barrels can be very different from each other. If you have worked for some time in well integrity, you know very well that the primary bearer is completely different from the secondary bearer. Even single elements are different from each other. So you can use this as a measurement unit. You can say that a person has 1.8 meters, 1.7 meters, because a meter is a meter everywhere. But you can say that the well has 1.5 barrel and expected everyone to understand the risk. And the reason well bearer elements are so different is because they have a different reliability. For instance, a cement plug is more reliable than a Parker, which is more reliable than a valve, for instance. The good thing is that you don't need to trust me on that. We have data to demonstrate which are the most and the least reliable bearers. Besides that, we need to understand how good are we treating the bearers. If you are testing, if you are inspecting, if you are giving the proper maintenance. So all these matter when you talk about reliability. And third, and maybe most critical for management, it doesn't consider time. You see, this is a static picture of the well. It's not the entire move. So the well can be green today, but what about tomorrow or 6 months from now? If you don't know how the integrity evolves over time, how do you expect it to be prepared for the actions required? I will give you a clear example of I just said. Instead of using a specific case, I'm going to use a technical note from ANP from the last year, where they are talking about the whole Brazilian industry. So ANP is the Brazilian Petroleum Agency, regulatory agency. We can see in this image that it was reported 559 wells with integrity issues. This number can seem much, but if you consider that we have probably around 10,000 wells, you will realize that there is a under notification of failures, with only 18 operators from more than 60 notifying their integrity issues, notifying their integrity status. That's why integrity status, it is still important for compliance and communication purpose. But the real problem comes here. You can see here in this graph the grace periods for those wells defined by the operators. But you see, 32 wells are blank, so they don't have deadlines to fix the integrity failures. Some are past due, and lots in 2024, indicating that they were postponed, several times postponed maybe. And some grace periods are very long, up to 8 years, and the agency is questioning this. It seems there is a lack of clear and risk-based criteria for grace periods. But the real problem is that those companies are not prepared, not ready to deal with this kind of problem, because our current system does not allow us to forecast the integrity of wells. As Peter Drucker's statement, we cannot manage what you cannot measure. In the absence of this, or in front of this apparent lack of definition from industry, the agency imposed some grace period for us. But they went from 8 years to a maximum of 1 year, some being 30 days. How do you expect the companies to be able to comply with this kind of deadline? I'm sure those are not based on a risk assessment. They don't consider that intervention in a well can add a lot of risk and expose people. If somehow we start to perform a lot of intervention, especially without appropriate time to planning, we could expect more incidents very soon. Let's give an example. Taking, for instance, this producing well with one well bearer failed, which give us 120 days of grace period. So it is important to note that the deadline imposed by the agency is 120 days, regardless of which well bearer has failed. I use QRA for a specific case of a subsea well to show how different failure produces different impacts and must have different grace periods. Of course, the results I'm going to show are illustrative and can vary according to the well being analyzed or even with the acceptance criteria. But for instance, if you took for instance the failure of the production master valve, as we have redundancies of valves in this path, it has a minor impact on the well integrity, and we are in the acceptable region, and we don't need to act. Probably the risk of intervention in this case would be worse than live with this failure, than live that way. But if you consider the downhole safety valve or the tubing, both are elements from the primary barrier, and their failure produces a tolerable risk, meaning that we must fix them, but at different times according to the impact of failure. So both failures are from the primary barrier, but they have different impacts. The tubing has a greater impact, so the grace period is lower. And finally, if you have a failure in the production case, it will produce an unacceptable risk, require intervention as soon as possible. Of course, we haven't seen the basic QRA concepts, but I brought this example just to illustrate both the limitations of the current system and how QRA can be useful, even for two failures falling in the same color, so both orange or yellow. This helps us to identify the criticality and adjust the response time accordingly. Let me briefly describe how I ended up dedicating my career to solving this kind of problem. Let my inspiration be your inspiration also. It all started in 2014 when I have the opportunity to work with Embraer. It's a Brazilian leader in aviation. And for 1 year, I immersed myself in their process, studying how they manage reliability. And what I discovered was truly eye-opening. The aviation industry has quantitative requirements to ensure safety, reliability, and performance. For instance, they have incredible high safety standards with the probability of a catastrophic failure during flight less than 1 in a billion flight hours. And they also set availability targets over 99%, which means less than 1% of probability of having a delay due to aircraft failures. These targets are just goals. They are integrated into every level of the supply chain, shaping designing, testing, and integration of components, as well as maintenance practice. So this is the aviation industry. But the following year, I visited a nuclear power plant and was introduced to their safety philosophy, very similar to ours, focused on integrity and barriers. They develop risk monitors using quantitative and real-time indicators to track the plant's risk. They had clear criteria for acceptable risk levels and used these insights to make a risk-informed decision, how to address failures, how to discuss with the agents about extension of plant's operational life. These experiences changed my perspective. While the aviation and nuclear industry had embraced advanced quantitative methods since a few decades ago, our industry relies heavily on qualitative systems like the traffic light scheme I showed in the first slide. I realized that if you could adapt these approaches to well integrity, we could dramatically improve how we assess and manage risk. From that moment on, I was committed to implement these ideas. And since then, I've been dedicating myself to this mission, developing quantitative risk assessment culture in our industry. A few years later, I mentioned 2014, 2015, I did this opportunity to know nuclear and the aviation industry. But a few years later, we have concluded the first part of the project. We have achieved what I envisioned, or at least I thought so. In 2018, I had my first chance to prove the value of the method. A friend who knew that I was working with reliability asked support in a well that he was responsible for. The well had a failure 1 year before, and the deadline for the intervention, according to the current internal standards, was about to expire. And they needed a few extra months to get the material ready for the intervention. So they wanted me to calculate if the risk of postponing the intervention was too high. And at the time, we haven't finalized the software, so we had to do the math using spreadsheets and Python. It took almost 3 weeks to run the QA. But we ran the QA, and we didn't have any criteria, quantitative criteria defined for the tolerance risk limits. So I had to improvise and calculate the normal or expected risk of the well to use as a reference. We can see this reference on the dashed green line, and in blue, we can see the actual risk of the well. The result of this analysis show that we could continue to produce the well for a few more months without exceeding the normal risk too much. We can see this on the final part of the graph. If we look at the past, we will see that the well had operated way above the normal risk a few times. However, if we implement a few mitigation measurements, we could produce for a few more months and reduce the risk as indicated in this orange line and operate under the normal risk. So I presented my case, and people were really impressed with the power of the tool I was showing. But what I didn't know at the time was that some people in that room had just finished developing our internal integrity management system, an enhanced version of the traffic light scheme. So they had just finished a 2-year work developing that system, and I was there present something different and claiming to be a lot better. In conclusion, I got a pat on the back, hear that someday they will probably be using QA, but at the moment they have decided to stick with the current system. So I'm telling you my experiences so it can motivate you, and maybe you cannot you not commit the same mistakes I made. So this was my first tentative of implementing QA in Petrobras. Of course, I was upset with the result of my endeavor, but instead of only mourning, I decided to learn some lessons from that. What I've learned from this case. First, to be more humble and understand that the quantitative and data-based decisions are a paradigm shift and will require a change in the organization culture. So I had to be more patient, of course. To enhance technically the system using the expert knowledge. Instead of ignoring the expert knowledge, we could take advantage of the expert knowledge and enhance the system, enhance the quantitative risk assessment. But most important, I need to transform a quantitative risk assessment into a management system. And what about the well? For that well, they rushed the intervention, and there were several problems during its execution. The intervention lasted more than 100 days. They handed over the well with half of its production potential due to some fish in the well, and the well had problems again a few years later. It's impossible to say, but perhaps if they had followed the study and had more time to prepare the intervention, the result could have been different. This was unfortunate for the company, but ended up reinforcing the potential of quantitative risk assessment. Even so, I took my lessons and worked hard to be prepared for the next opportunity. 1 year later, I had another one. They called me with this problem on the screen. They had to install a new packer in a well because of a failure of the old one. But because of the depth, this packer would be installed in a zone with no well cement. So the primary and secondary well barriers would have a common case section, as you can see in the picture. By our standards, it would not be acceptable to leave the well in this situation. There were therefore two other options. To remediate the cement, so it could be possible to create a new well barrier above the packer, but a circulation squeeze is very risky, time-consuming, expensive, and there is no guarantee of success. And another option would be to install the new packer inside the liner, but this would require removing the previous one, and we need to wait for the acquisition of such a packer. Besides, it would cause a flow restriction. So they want me to analyze the three options using quantitative risk assessment. The good thing about this case is that I did not have to use any acceptance criteria, as we could just compare the three scenarios. And the issues in the last intervention made people more open to QRA also. So at this time, the luck was on my side. You can see the results here with the probability of integrity failure over the next 10 years. If you try hard, you were able to see that there are three different curves. The risk was virtually the same for the three scenarios. We ran even an uncertainty analysis, as you can see in this zoom, and the result of the three scenarios don't differ statistically. So the result is the same. The three configuration presents the same result about risk of integrity failure. More than absolute numbers, sometimes quantitative risk assessment can give us other insights, such as importance of individual elements to the total risk. Here we can see that the shared production case section, which was the concern, is contributing very little to the total risk. We can see here is the element in importance and contributes almost 10 times less than the first one. You can see in the table. This time, everyone accepted the results of QA, and more importantly, we were able to change a decision that had previously been made, generating value for the company and even reducing the risk and people exposure. So it was our first victory. And the result was so great that the corporate manager for Well Integrated decided to provide the means to create a strategic program at Petrobras called the Well Risk. The Well Risk program was created with 4 pillars, and I'm showing this so you can understand the challenges in implementing quantitative risk assessment into our organization and how we address those challenges. So the first pillar was the mathematical model that I was developing at the time. But more important, to develop software, computational tools. We cannot expect that we're going to spend 3 weeks programming in Python to run a QRA. So we developed friendly tools and integrated them with our whims. Secondly, we have a culture of decision-making on pure judgment and using only qualitative and simplified tools to support us. So, to cross this gap and reach everyone in the organization, we have offered training courses with different degrees of complexity and organizing several workshops to discuss QA with everyone involved in well integrity. The third pillar is data. Data is the raw material for quantitative analysis. So we invested in international databases, but also we developed internal databases, reinforcing with people the importance of registering data, of recording data, and share data is very important. And more recently, we developed a tool, special tool to elicit expert opinion when necessary. So we can use expert opinion in our quantitative risk assessment. And finally, we have to change some internal process and standards and create new procedures to run quantitative risk assessment. If you remember the first case I presented, one of the reasons for not using quantitative risk assessment was that people felt uncomfortable using something outside the standards. Now we are trying to make this even a national best practice. As Jovan mentioned, I'm working right now with a group in IBP, Brazilian Petroleum Institute, writing the best practice for risk assessment applied to well integrity. So we are going to put one chapter dedicated to quantitative risk assessment. But my focus here will be on the software and how we develop a management system based on quantitative indicators. Here, I will show how we use quantitative indicators inspired by the nuclear industry to manage our wells. The first two layers access the current state of integrity. We can see the parallel with the nuclear industry. While the nuclear industry is concerned with the core damage frequency and which one can evolve, this core damage frequency is actually measuring the loss of integrity in the reactor core and those that can evolve to a large radioactivity release. We develop similar metrics, but focus on the well integrity. So we have the well integrity level that measures the failures in the well integrity and the ones that can be evolve to a large hydrocarbon release, or what we call blowout risk level. And to prevent loss of containment or blowout, we have to give proper maintenance after a failure occurs, which is indicated at the third level. So we use the concept of incremental cumulative risk. Every time a component fails, this triggers the incremental cumulative risk. At this level, we define the response time to repair the failure by limiting the maximum incremental or additional risk that a failure can impose on the system. Will be more clear in the next slides. Let me show how we use this to create the risk monitor, which is integrated in our databases and monitor system. This saves a lot of man hours when discussing well integrity. The operator can supervise all the wells in operation, and we can see the ones that are in safe conditions, the ones that are in an acceptable risk level, which will require intervention as soon as possible, and for the wells that are in a degraded condition at a moderate risk level, the failure manager will be activated, indicating the time to reach the maximum incremental risk. So as the analysis is quantitative, we can access the time left to reach any one of these limits, allowing us to plan and prepare the proper actions and resources for risk mitigation, which has proven us to be more valuable than just classifying the wells. And how this work? Here I brought 3 illustrative cases. The first case is the expected trajectory of the well. As time goes by, the aging effects move the well to the right, increasing the failure frequency, but at the same time, the severity tends to reduce due to reservoir depletion. A second case, undesirable but easier to analyze, is when the failure is so critical that makes the risk go to an acceptable risk level. So in this case, we should perform an intervention as soon as possible. And the third and most difficult scenario is the single well bearer element failure, leading to the risk to the moderate region. In this case, we need to take some action, but the time to respond is not immediately. So the repair time or grace period is given by the incremental cumulative risk, as we can see in the 2 examples here. This orange area is in the graph is the original risk of the well before the failure. After the failure, the risk increases, and the incremental cumulative risk is the area between the original risk and the current risk level. So we have the incremental cumulative risk, and this area measures the additional risk caused by the failure, and by limiting this area, gives us the grace period. The worse the failure, the shorter will be the time to repair. We can see this in the second example. So regardless of the acceptance criteria being used, this will make act sooner in the worst failure. So this makes us act on the worst failure first, basically. So that's the concept of incremental cumulative risk in these 2 examples. But let me show you the software right now. Here you can see the screen of my Bear software. It was developed in partnership with DNV by people who have been working with QRA and reliability for more than 40 years and had previous experience in the nuclear industry. We can see, so I have been showing a lot of points in that graph. If you select one of that points, one single well, we can see this screen. We can see the well integrity level over time for a specific well. What you see here includes the current level. You can see in the graph the current level of well integrity, and we can see the past information. We can see historical behavior of the well. The fluctuations we see in the graph represents the impact of tests and inspections performed. But it doesn't stop there. The model also forecasts future performance, enabling proactive decision making. For the first time, we are not just reacting to well integrity problems, we are anticipating them. This model also allows us to evaluate the impact of failures. We can observe the integrity levels before and after failures, showing their criticality and associated risk. So even for 2 failures falling in the same category, in the same zone, we have different well integrity levels, so we can assess their criticality and associated risks. We can see in the left summarized information such as the well integrity speedometer, offering an immediate view of the status of the well and a breakdown of the key metrics. If you want, you can use even the, let me put here, you can use the light scan to help to see whether the risk lies in the acceptable, moderate, or intolerable zone. But this is where the power of the model becomes clear. As I mentioned, even if 2 failures are in the same region, you can compare them quantitatively now. This is more just a tool. This is a paradigm shift. By quantitatively answer the fundamental question about well integrity, the system empowers company to make better, faster, and safer decisions. I will now, now that we have seen how the system, what the system can do, I will briefly explain how it works, what happens behind the scene to turn raw data into actionable insights. To perform quantitative risk assessment, we first need to model the configuration of the well. This process begins with the well bearer schematic and mechanical drawing, where we can see in this picture. From this drawing, we can see the cavities and barrels in the well. So the cavity and barrel diagram maps all possible leak paths from the reservoir to the environment. These numbers in the figure represent internal cavities, while the boxes indicate failure modes that can communicate between these cavities. This diagram forms the foundation for understanding the pathways through which leaks could occur. We can also see how limited is the two-well barrier concept. Let me put here, we can see how limited is the concept of two-well barriers, covering only a small part of the well complexity. The second step is to map all potential leak paths. So you can imagine to be an oil droplet trying to escape from the reservoir to the environment. To do so, it must travel through a series of barriers. Each leak path represents a combination of failures that must occur for the leak to happen. For example, one possible path could involve a tubing leak followed by an external leakage in the wellhead. In a typical well, we can have dozens of failure modes and hundreds of potential leak paths. So it's very complex to expect that an expert could just evaluate the risk without going into details. So even we are still qualitative, but look how much detail the model is right now. Some paths might involve just a few failures, while others can involve several failures. The longer the path, the lower its probability and contribution to the total risk, as more failures need to happen. And the third and last step is we need to, once we identify the leak paths, or as we call in reliability, minimal cut sets, we can quantitatively evaluate the failure. This is done using appropriate equations, some to aggregate the components in the minimal cut sets, and others to aggregate all the cut sets, which are not in the scope of this presentation, but you can find in the paper we published. But each component contributes with its failure rate and its unavailability. Most reliability models available consider for simplicity only the constant failure rate or exponential model. But to consider the aging effect, our model allows the failure rate to increase over time by using the viable model. And we rely on data from multiple sources, include both generic and international databases or internal databases, structural reliability, physics of failure, or even expert opinion, as I mentioned. And the unavailability of the component considers, besides the failure rate, considers the replacement history, when was the last maintenance, the last time it was tested, or whether it's being monitored or not. So everything in the model in real time, in the well, in real time is considered to run the quantitative risk assessment. Now, to go to the last part of the presentation, I'm going to show a real case of application after we develop the software. In this screen, the above graph indicates the well. Let me use the laser point. So this upper graph indicates the well integrity level. The green line represents the original risk of the well with the periodic tests, and we can see also the aging effect over time. But after 6 years of production, the SCSSV fails and increases the risk. In the second graph, we can see the additional or incremental risk start to accumulate. And this gives us the first grace period based on the limit of the incremental cumulative risk. So we have the deadline to repair the first failure. But before we achieved this deadline, we had a second failure, this time from the gas lift valve, which increases even more the risk and makes the additional risk accumulate faster, reducing the grace period. So we can see how KIRA A supports us to determine the grace periods in a risk-based way. Continuing, but once we have decided, you can see in this graph the deadline for intervention. Once we decided that, we need to think about the best strategy to repair the failure. And let's see our options in this case. We could, of course, do nothing and allow the current situation to extend until the end of the lifespan of the well. Or we could perform a heavy workover and replace the whole tubing, the whole completion, fixing both failures and producing the best result after the intervention. Or we could perform a light intervention and replace only the gas lift valve, producing an intermediate result. And using our analytical module, we can compare the risk of those three different strategies. If you decide to live with the failure until the end of the lifespan of the well, would result in a risk of 5.89 10 minus 3, as we can see in the graph. With the heavy recover, we produce the less risk after, but in this case, we must add the risk of the recovery itself. The final result is still better than doing nothing, for sure. But let's investigate the third option, the light recovery. The risk after recovery will be something between the two previous strategies because we are repairing only one failure. But the advantage of this strategy is that the light recovery takes less time and much less risk than the heavy recovery. So in total, this is the best strategy, both in terms of risk and efforts. So the QA allows us to determine both the moment and the best strategy for the intervention. And just by curiosity, to calculate the risk of intervention in the previous slide, we use the intervention module, where we have two options. The simple model uses average frequency of blowouts for different types of intervention. This is based on databases such as the IOGP report or even the SINTEF blowout database. It's very useful when we need a quick comparison or we don't have enough information about the intervention. But we can use the detail model, so we can create the intervention and access it to risk. It's hard to see in this image because the intervention has a duration almost negligible compared with the life of the well. But if you zoom in, we can see the intervention steps and how risks varies over time during the intervention. And we can do this by adding all the activities planned during the recovery and their schedule. We have a lot of predefined activities, but you can create new activities and define the well-bearing elements in place during the activity. The good news is that now, if you have a new technology capable of simplifying the recovery, we can see the impact on the intervention risk. For instance, if you had the insertable CSSV option in the previous case, whose risk of being installed is considerably lower than the heavy recovery, we could have decided that the best solution was to repair both failures. So we can now understand the risk in detail of the intervention. And another feature of the system is providing a high-level overview of risks and production that can support the prioritization and planning of what to do with the wells. So if you look at this panel, we have a sample of wells from different business units, their risk and their production. This can easily support high-level strategies to manage the wells. For instance, we have wells with a high production and a high risk that should be considered as priorities for the well intervention. The wells that have low production but high risk should be considered candidates for P&A. Some wells don't impose a high risk to operation, and neither are high producers. So we could think in methods to enhance production, like this one. And finally, we have our dream wells, which production with low risk and high production. And we just need to keep monitoring those. But this was only possible because we created ways of measuring risk. Without measuring, we cannot manage. And in the next webinar, to be scheduled soon, I'm going to expand the concept of risk, not only for well integrity, but we are going also to talk about costs and availability. In other words, efficiency. We are going to discuss concepts such as life cycle cost analysis and reliability, availability, maintainability, and safety analysis or runs analysis. We are going to discuss how to incorporate the conditions of the well to go from risk-based to condition-based analysis. This will help us to understand the difference between remaining useful life and remaining safe life. And we are going to see how to use this in the P&A planning. And finally, I'm going to show our final destination, the Wisdom Project, which aims to combine all the analysis in one single software. And to finish, I would like to close this presentation with a thought. What is risk? We discuss a lot about risk and how to measure it. But let's understand an important thing. Look at this image. Do you consider this overtaking safe or risky? If you are a normal person and not a speed racer, you probably would find this very risky. But what about now? Notice how the situation has not changed at all. But the use of technology and data allow us to see ahead and reduce risk. So risk is not just about the situation, but about our ignorance on the situation. So I genuinely think the only way we continue to survive as an industry in the next decades is by using data with quantitative risk assessment to reduce the risk for the environment and for the society, being safer, more efficient, and being prepared to take care of our wells. So operational readiness is really important so we can manage the 1/3 of wells that has integrity issues. And we can do this reducing at the same time the number of interventions and the man hours effort to manage well integrity. And besides that, I really think that young people who are starting in our industry can find this approach way more interesting than having to wait 20 years so they can have enough experience to be part of decisions. So my goal on this presentation was to encourage each of you to embrace this new paradigm, to embrace the quantitative risk assessment into our own organizations. Take the learnings from my own experience and apply them to your wells or any other critical asset. You don't need to start with all the things in place. You just need a case and the willingness to apply QA. And I can help you with, I can help you. I'm available to support. You can get in touch with me. There are my contacts. And let's work together to transform our industry and ensure a safer environment and sustainable environment for the future. So thank you, and let's make it happen.
Fantastic. Thank you, Danilo. You're muted there, Giovanni.
Yeah, thank you, Danilo. Really, I enjoyed in listening you and the challenges which you had in your work and together with your team. Really, as you said, there is a room for improvement of how the people are looking, how the operators looking on well integrity, and how to manage, make a decision, and on the end, everything of that will end up for going through the best decision in that moment for us. Saying that, I have a question. Consolidating all of these things, what is your opinion on the example life well extension? Yeah, this is something which some governments which are, let's say, more advanced, more ahead, and having those guidance already implemented in their systems, encouraging operators to have and respect the deadlines to fix well integrity problems. As you said, we are, even if we are in the middle where we are either orange and yellow wells, which we need to fix. You said that is different timeline is for different operators because we have different people working on and different targets. So how you can see if governments can influence operator to respect those deadlines and to not further extend well integrity problems on the particular well. Danilo, you are muted.
Oh, again.
Again.
Sorry. Yeah, thank you, Jovan, for your comments and for the question. We are going to explore a little more about this extension of life extension for wells in the next presentation. I think we have a lot to contribute using quantitative risk assessment for this. But I've been seeing that this question about the government or the regulatory agency influence the industry is a two-way street. So for one hand, we like to have the freedom to make our own decisions, but for the other, on the other hand, we need to demonstrate to the agents, to the regulatory agencies around the world that we are capable of doing so. Because the example I'm sure about the technical note from the ANP last year shows that the agent is not so content with us, not so happy with us, because we are not reporting correctly, we are not demonstrating our capabilities of calculate or determine our own grace periods. So we are constructing a path where the agency will start to impose some prescriptive rules to the operator. So we need to discuss, and my intention in this best practice we are doing here in Brazil is to open the channel with the agents so we can discuss how you can apply these data-driven decisions to determine the deadline to repair the failures in the wells, or even how we can use this to extend the life of the wells. So we are living in two different worlds. Some way we're talking about new data, new technologies with data, machine learning, and on the other hand, we're still struggling to get data to use even the scholar system that I presented on the first slide. So it's a complex world we live in right now, and I'm going to discuss a lot more in the next presentation, especially the difference between remaining safe life and remaining useful life. I think this is very important for companies to understand.
One question from Simon Copping is about how long it takes to perform a detailed risk analysis on a well, Danilo, and I'll add to that one question I had on my own also. So you're presenting remarkable work from a company that has invested a lot in that area. What do you think would be a roadmap for smaller operators that don't necessarily have built the same expertise in-house? So how long would it take for someone to gradually apply QRA, maybe to their tricky-ish, the more tricky wells initially?
Okay, perfect. About the Simon question, how long does it take to perform a detailed risk analysis? So right now we have implemented this software connected with our wings. So we don't need actually to go there and run the QRA analysis anymore. Every time you go in our win system and we put a failure or we put a test in a well or we change something in the well, or if you perform an inspection on the wellhead or the Xmas tree, every time you put new information on your win system, this goes automatically to the quantitative risk assessment. So every day it runs all the updates. But of course, sometimes, as I presented a few cases here, we would like to simulate possible scenarios or to compare different strategies. So in that case, we can take some days to model all the cases and create possible scenarios, especially if you want to detail the intervention, as I mentioned. So this can take a few days if you have people trained in our organization. If you have someone that don't know how to do, it will be taking much longer, as you mentioned. And I think for other companies to start on this path, uh, we don't need to think at the beginning to have the system running for 100% of the wells. We can take the most critical wells, the ones that right now are in the red or orange region, and we start with a few wells. And you can start doing this by hand, as we started a decade ago, or you can look for partners. We have available softwares, not only this one I mentioned, but we have other softwares available to run QRA. Someone more specific and someone more generic, so you have more work to implement the quantitative risk assessment. But as I mentioned, if anyone decide to go in this path, we can talk more. You have my contact, and I will be willing to help you. I'm not commercializing anything here. I'm an operator, so I work for an operator. So I just want to change the way we manage wells in our industry. So, and I think it's very important if somehow we could get together and start to discuss and to write best practice to serve as a guidance for other industry that want to implement these strategies.
Very good.
Uh,
We've reached the 1 hour mark and exceeded that. Jovan, any final comments or thoughts or questions?
Really quick one, really interesting, because we are driven by planning and looking ahead. Danilo, did your team and you develop also selecting different strategies, as you said, going for the heavy workover or light workover to cure the well integrity problem? Can you quantify also the value of the intervention, and then on a big pool of the well on which software is looking, you can selecting different strategy, you can get maybe a value which is planned for the next period for the well integrity, curing those issues?
Yeah, about that, again, I will talk a little more about that in the next presentation. We have a new software that doesn't only look for the risk, the well integrity risk, but also the impacts of intervention, both in terms of risk, costs, and also in the production efficiency. So we can set different strategies, not only for a single well, but for the whole portfolio of wells. And we can compare those strategies at a high level. So maybe if I put way more interventions than necessary, I will have an increase in the risk because intervention has risk. I will have an increase in costs, and maybe I'm going to produce less. So you can compare all these indicators in a life cycle cost analysis for the whole field, not for one single well. But again, I will explore these much more in much more details in the next presentation.
And I
Yeah,
think it's a
really
great,
looking forward.
yeah, it's a great teaser for the next presentation, Danilo. I did take away that the way you assess the reaction time comparing various scenarios is highly dependent on people competency. So you need good teams to look at the various options, that they're reasonable, they're well built. So you feed your decision making process with quality teamwork to a degree.
Yeah, when I started on this journey, I was only thinking about technical challenges. And what I discovered is that sometimes the organizational challenges are much higher. You need to convince people, you need to make people understand, because if you don't understand, it's difficult to accept some results. And now we are in the next level. We are discussing with agencies. So at the same time, the agency loves this kind of analysis because it removes some bias of the operator, but they need to understand also. They are questioning from where this data come from, it's representative or not. So it's a continuous challenge that I've been facing for many years. So yeah, you are right.
We look forward to your continued the second part of your presentation.
So thank you again for inviting me, and thank you for the audience for patience. So thank you very much. Have a
Oops, sorry, I cut him. So yeah, we'd like to thank you for joining today, Danilo in particular, and the audience for the questions and comments. We hope to see you again at our next webinars, and we'll now conclude the event with a short video from SPE.
You know, people ask me why they should join SPE, and what I tell them is that SPE is absolutely essential. Frankly, if SPE didn't exist, somebody would have to go out and create it. When you graduate with a technical degree, a petroleum engineering degree, or other engineering degree, you get a lot of really good knowledge that gets you started on your career, and you learn a lot on the job. But the jobs that we have in this industry, they're really quite difficult. And you've got to have other resources, either to solve specific problems you might be having at the moment, or to better understand how to solve, daily issues that you work on. SPE provides opportunities to learn about new things that people are working on. There are great articles in JPT Magazine and the other magazines that we have that are really useful. If you're not reading JPT every month, I tell you, it's essential to do that, to keep up with the technology. We have excellent conferences where you can learn from people who have solved very difficult problems in our industry. And doing that is just incredibly important and incredibly useful. To me, I don't see how you can be an engineer working in the petroleum industry and not find value in the resources and the opportunities that SPE provides. It's an opportunity to meet people who can help you in the industry, and it's an opportunity to get the knowledge you need to be successful.